I'm not going to do it.
If he does, then the mouse will.
Please, I see my stuff back.
I will before.
Alright.
Oh, that. I don't know. We'll talk about it.
Okay.
Okay. So on Friday, we were talking about a point of concurrency for our perpendicular bisectors of a triangle. Now, we talked about all three perpendicular bisectors, but we really only need two. That's usually what we go by. Because if I have two perpendicular bisectors and they're accurate, then the third one is also going to go through that point as well. Does that make sense?
Yeah.
So a lot of times, just to eliminate some of the visual confusion and clutter that is created by all three, a lot of times we just put any of the two in. Okay? But that point that it's going to create, we talked about that being the circumcenter, right? And what that point is that it is the location that makes the distance from A to that point the same as B to that point as it is C from that point. Okay, so that is the point that is equidistant from all three vertices. Okay, it will allow us to create a triangle, or not a triangle, a circle that contains all three vertices of the triangle. Okay, so every single triangle has one of these. Okay, so that is the circumcenter for this situation. So now, here's one feature that I explained to you. If I know that my circumcenter is on the inside of the triangle, what kind of triangle does that have to be? I have no knowledge about the angles, but the circumcenter is on the inside of the triangles. Anybody remember what kind of triangle it has to be then? It has to be acute. Okay? If my triangle is a right triangle, where does that circumcenter fall?
It's on the midpoint of the hypotenuse.
It's on the midpoint of the hypotenuse. Okay? So if I were to know nothing about this triangle, nothing about angles, no markings in the angles or anything, but they tell me that that point D is the circumcenter, you can automatically now say that you know you have a right triangle. Okay? And it doesn't allow me to determine what the acute angles are, but it does tell me that I do have a 90-degree angle. And then when it's obtuse, that point is on the outside of your triangle, and that means then that my perpendicular bisectors, that's where they cross, is on the outside. Okay? So you can kind of see as we go from acute to right, what's going on? I'm missing a, there we go. Acute to right to obtuse, that point kind of migrates from the inside to on to the outside. Okay? But there's always that circle there that is centered at point D and is passing through the three vertices of that triangle. Is that okay with everybody? Okay, that is referred to as the circumcenter. The other type of bisector that we've been talking about is an angle bisector, correct? So let's see what happens with an angle bisector inside a triangle. So we take angle BAC, I'm going to bisect it. So that right there cuts angle A into two smaller congruent angles. Is that okay with everybody? If I do the same thing for ABC, and then do the same thing for ACB. Okay, we get this point right here, no matter what my triangle looks like. Okay, if I go, it's acute, now I go to there it's right, and there it's obtuse. What is that telling us about that point right there? It's always where? It's always on the inside. So whatever we're going to call this point here in a moment, it's always going to be on the inside. Okay. Now, if you remember, what we said last week was if we've got a point on, let's say, that blue angle bisector. Any point on that blue angle bisector is going to be the same distance from those two blue sides. So this point right there, its distance from BC and its distance from BA right now is the same. Does that make sense, everybody? And that distance is found by traveling from here, perpendicular, down here to BC, and then from here, perpendicular to AB. Okay, so maybe that looks like the segment that'd be perpendicular. Okay, but those two distances have to be identical. Okay, well then, the idea is, well, what if we look at that angle bisector? Then any point that is on that angle bisector is going to be equidistant from those red sides. Okay, so F is going to be the same distance from AB as it is from AC. Is that okay with everybody? Well, if we look at maybe a point D, okay, and that is a point that is on the blue angle bisector and it's on the red angle bisector, right? That means that point D, because it's on the blue angle bisector, is equidistant from AB as it is BC. And because D is on the red angle bisector, it's also equidistant from that line or segment and that segment. So through the use of the transitive property, then, it says that D is actually the same distance from all three sides of that triangle. Does that make sense? So if I just gave you point D right there, and we're going to label that as point D is called the incenter. Okay, and it is the point that is equidistant from all three sides of the triangle. So I can show those distances. It takes a little bit of time here to actually generate them. Okay, so that distance GD is what we refer as the shortest distance from D to this red line AB, and that is currently 3.28719. Okay, change the rounding here so it doesn't take up so much space. 3.29. Now I'm going to find the same distance, so I'm using perpendicular lines, so from D perpendicular to there, and then I only want to go to the blue line, so I got to find that intersection point, so it's going to give me the segment DH. If I look at DH, its length, 3.29 again. Is that okay with everybody? So hopefully that shows you that that point is at least the same distance because it's on this blue angle bisector. It is the same distance from the two sides of the angle that blue line bisects, right? Blue segment bisects. Now I'm going to find the distance from D to that line. Find the intersect point. Get that segment. And now if I ask it for D to J's distance, again it's 3.29. Which means then, because this distance was 3.29, that distance is 3.29, because it's on this red angle bisector, it is equidistant from the two red sides. Well, when we do this, we get all three of those to be 3.29. So if we do the same thing that we did with, just looking for a letter that I haven't used here, that we did with the circumcenter. 0 to 360. Okay. I'm going to rotate that segment around the end center. And would you guys agree that there's a circular motion that's being made there?
Yeah.
If we were to trace this point G prime, we can see the circle that is created. Okay. Now that circle is referred to as the inscribed circle or the end circle. Okay. Might be a good thing to write that down. So let's see here. I don't know where my marker. There they are. Okay, so that point D was the end center. The circle is the inscribed circle, or referred to sometimes as the end circle. The way I remember N means, like we know what N means. Scribed is drawn, so it's drawn on the inside. Okay, now circumscribed was the one that was drawn on the outside, but there has to be some mathematical components to those definitions. So what are we seeing that the inscribed circle ends up doing to these three segments of the triangle? It connects to all three. Now, how many times does it intersect each of those three segments? Just once. Okay, so let's see here. I'm going to clean some things up here with these segments, these 3.29s. Get rid of those. Let's get rid of all these points except for F. I don't want those. We don't need D prime. I don't need I. All right, so if I look at this information here, and I just draw that circle. Okay. What is happening here is that this circle is only touching this triangle at three spots. If I zoom in here on H, okay, as close to H as possible, if I zoom in far enough, we're going to find out if GeoGebra has the computing power, and it does, that the segment of the triangle and the circle do not touch there, right? Does that make sense? They're separate lines. It is only at H you won't be able to see this because of the way this works with zooming in, but I should be able, if I move away from H just a little bit, oh, there's the issue. So at some point, GeoGebra start acting bizarre on me, bouncing around just because of the level of zoom that we're currently at. But if I keep zooming in on there, you're going to find out, if we had the power, that there is a separation between the blue segment and the black circle. Okay? But if I zoom in strictly on H, they're shared. Does that make sense? That is the same point on the blue and on the circle. Same thing with J up here. Same thing with G. Okay. Does anybody know what it means, or what the word we use for when we have a circle that touches a line at one point and one point only? If I take this circle here, so let's say I take a dinner plate, and then I take a ruler and I put my ruler right next to the dinner plate and they're touching. they should only be touching at how many spots? Only at one. Okay, so they're intersecting twice, right? They're intersecting twice, but like maybe right there they're only intersecting once, correct? There's actually a word for that. And that's that one line. So the one I chose was a little bit off, if you look where N was. This is referred to, that line right there is referred to as a tangent line. Okay? When a circle and a line touch one time and one time only, they're referred to as tangent to one another. Okay? Have you guys ever heard of the word tangible? What does tangible mean? You guys have savings accounts for banks? Okay. When you see that, when you log into, let's say you log into Chase Bank and you see your account number and how much money you have in that account, is that tangible money to you? Can you touch that money at that moment? Can you put it in your pocket? No. Okay. But if you open your wallet and your savings is in your wallet, can you touch your savings? Yeah. So your savings there would be tangible to you. Okay. Tangible in like the English language means to be able to touch. Okay. Or to hold or something like that. You hear people talk about, if you ever watched like people analyze athletes, they'll say that they have the intangibles. Okay. Intangible means not tangible. Does that make sense? Not touchable. So like leadership, work ethic, those are things that are kind of like the intangibles. Does that make sense? So tangent in mathematics means we can touch one time. Now, we can have a lot of, we talk about circles being tangent to lines, but we can actually have other, I could look at two circles, and we'll talk about this in a lot greater detail later on, but those two circles would be tangent to one another. Okay, those two circles are not touching more than once. Okay, we can have, this is exactly what we do in calculus. Let's see here. All right, so in calculus what we do is we take a curve, and it doesn't matter what that curve looks like, but what we want to do is we want to look at like the slope. Like if you're standing at point A, like think about that slope. If this is like a hill, like in your backyard or something like that, something pretty dramatic. If you're standing at point A, you've got a pretty severe slope there, right? Okay, it's harder for you to get up that curve at A than maybe it is if you're standing at like B. B is not such a drastic slope at A. If I'm standing at B right there, then I have like zero slope, right? Does that kind of make sense? If I'm standing at like B there, now I'm kind of falling down. Kind of like if I think about it as like I'm on a roller coaster. If I'm leaning back on the roller coaster, like at A, okay, I've got a positive slope, and it's right now a steep slope. If I'm at B, it's kind of like being at the top of that roller coaster. So you got a zero slope. You're not going down. You're not leaning back. You're not leaning forward, right? If I'm at B though, there now I'm leaning forward, correct? So the slope of lines that we've learned through algebra, they're always the same. The slope of a line is always the same no matter what in algebra. Okay, but the slope of a curve is always different. Okay, so if I look at, we'll just use point G here. I don't think that'll, there we go. If I look at a tangent line through G, okay, so what we do is we talk about tangent lines. If I want to know the slope of this purple curve at A, it's going to be the slope of that line right there, 6.36. If I wanted the slope up here where I said we were kind of at a standpoint where we weren't going forward and we weren't going backwards, okay, the slope, remember, is it's the slope of this line, this tangent line. It's the x coefficient. There's no x here, right? So the slope would be 0, and that's the idea that we're not leaning back, we're not leaning forward. Here at point B, the slope of the curve there would be negative 2.24. So that's kind of what we investigate in calculus. And the reason I talk about that is because some of you will take calculus. And what I need you to understand is that the mathematics that we are taking at 9th grade, 10th grade, 11th grade, they all culminate at calculus. Does that make sense? So there's going to be concepts that we talk about in 10th grade, 9th grade geometry that we have to be able to retain so that when we get to calculus, we're not trying to relearn the geometry and then the algebra and then the calculus. Does that make sense? Okay, so that's what we call a tangent line. And again, we'll talk more about tangents in, I think it's chapter maybe 12. Start talking about circles again. All right, so I'll let you guys write this down if you don't have it already, but it's the concurrency of the angle bisectors. It says the bisectors of the angles of a triangle are concurrent at a point that is equidistant from the sides of the triangle. Okay? It's exactly what we just went through on that GeoGebra activity. It says the point of concurrency of the angle bisectors is called the end center. Okay, the end center. Whenever we talk about, we're going to use these words circumscribed and inscribed a lot throughout the rest of the year. Circumscribed means the circle has to be on the outside. Okay. That being said, it just doesn't have to be any circle on the outside. So if I have like that triangle there, that is not the circumscribed circle, because the circumscribed circle has to be on the outside, but it also has to have all three vertices of the triangle on the circle. Does that make sense? Same thing for the inscribed. If I draw that triangle and then I draw that circle, even though that circle is on the inside of the triangle, it's not the inscribed circle because it doesn't touch all three sides one time. It's not tangent to all three sides. So that's the kind of the mathematical component that we need to add to the word circumscribed and inscribed for our applications. Okay. There's going to be, you need to inscribe, you need to have your circle tangent to all three sides, and circumscribed, your circle needs to contain all three vertices. Now, when we talk about inscribed and circumscribed, again, they don't have to be just triangles. Just kind of give you, or if I give you a circle like this, and we put a series of points on here, that would be an inscribed quadrilateral. Does that make sense? The quadrilateral is on the inside. And the circle would be called the circumscribed circle because it passes through all the vertices of that quadrilateral. Does that make sense, everybody? Okay. You have maybe seen this a little bit when we've talked about, let's say I have a hexagon and I want to find the center of that hexagon, so I'll just do it that way. And then there should be a circle. So this is what we call a regular hexagon. But there is a circle that passes through all 6 of those vertices, right? Okay. That is actually I don't know if we've talked about this, but that's the reason why we know that there's 360 degrees in a circle, or that we attach 360 degrees to a circle. Have we talked about that before here?
No.
How many degrees? So if I look at this hexagon real quick, can we take this hexagon and break it up into do that, and do that? So does that give me 6 triangles in here? Mm-hmm. You know anything about those 6 triangles?
They're all blue.
Okay, so if I look at, they're all congruent triangles, and if I look at that distance, that distance, that distance, what does that tell us about each one of those triangles?
Every side of the triangle
Okay, so it's an equilateral triangle, right? And if it's equilateral, what's that tell me about the angles? They're all 60 degrees, right? So this angle where my cursor is 60, this one's 60, this one's 60. Well, if this angle right here is 60, and all 6 of these triangles are the same, what's this one? 60. What's this one? What's that one? What's that one? What's that one? So what's 60 times 6? 360. So if we remove then the hexagon, should there still be 360 degrees there? So then if we remove, if we remove the segments, is there still 360 degrees there? So that's where we get the idea of 360 degrees for our circle. Okay, and I believe it was the Babylonians that that 360 actually comes from, because they didn't know when they first started out 360 degrees, but they knew that they could circumscribe a circle around a hexagon like that, and they knew information about the hexagon. So then that allowed them to attach that information to a circle as well. So what you're going to see in your homework, guys, eventually, is questions like this where they say, they just give you markings in a triangle, and you have to decide what do those markings, what are they talking about? Okay, are they giving me the circumcenter, or are they giving me the incenter? Okay, and right now, because we can look at this marking right here, and that angle are congruent, right? Does that make this segment right there an angle bisector? Okay, and then we can do the same thing up here. This angle there and that angle there are congruent. So does that make this an angle bisector? Okay, so what's that tell you about point G? Point G is a what? Point G is an incenter. Okay, so if it's an incenter, then it means it's the same distance. That means that that distance right there is the same as that one, which is the same as that one, right? So those 3 blue distances are the same. And what we're seeing is that one of them is GB and one of them is GD. So if they're all the same, what should I do with those two? All right, so 8x minus 7 equals 5x plus 8. And we should be able to solve for x, right? And once I solve for x, can I then plug that back in to find GF?
Yeah.
Okay. But is there anywhere to plug it in to find GF? No, so what do I do? If I do this, I think I get x to be 5, don't we?
Yeah.
So I get 3x equals 15, x is 5. There's no GF to plug back into. And GF,
Isn't it just GB?
yeah, that's that segment, or it's that red segment, which is the same thing as GD or the same thing as GB, right? So I can plug back into any one of those, GB or GD, evaluate, and that's going to give me, what, 25, 32? 33? So give me 33, which is the same distance as GF. Does that kind of make sense?
Yeah.
Okay. Let's see here. I don't know if I've got any. This example here, I always like to talk about this one. So let's find the circumcenter. So this is what we're doing on Friday. Of those 3 points. Okay. Now, if those 3 points are not orientated in a specific way, you have to create equations of perpendicular bisectors to find this point, which is a nasty, tedious task. Okay? But if we look at those, because this point here and that point there have the same x value. If they have the same x value, how do those relate to each other in the coordinate plane? Okay, so these two, these red ones that I've underlined are on top of each other. Does that make sense? In the coordinate plane. So like -5, -4 would be maybe there. -5, +4 would be there, right?
Yeah.
So that's going to be AC. And then this one here and that one there, because they have the same y value, they are horizontal to one another, right? So negative 7, 4 would be maybe there, correct? So there would be the B. So how do these relate? This is where they come together and they make a right angle right there, correct? And that's what Dax told us. So if that's the case, where does the circumcenter occur for a right triangle? The midpoint of the hypotenuse. And the hypotenuse is segment AB, right? So you guys remember the formula for finding the midpoint being x1 plus x2 over 2 and y1 plus y2 over 2? If I take my x's, add them together, I get negative 13. Sorry, negative 12. And what's negative 12 divided by 2? Negative 6. And I add my y values together and divide by 2, so it gives me 0 divided by 2 is 0. So give me 0. And I'll give you a quick, just so you can see it a little bit easier in distances, kind of mesh. So if I go A is at negative 5, negative 4, B is at negative 7, 4, and C is at negative 5, 4. If I put those together, put my axes in here. Okay, that's the picture we drew by hand, right? Okay, if I ask for, I don't know if there's a circumcenter button on here. I don't think there is. But if I want the midpoint between B and A, is at negative 6, 0 that we found. And now that circumcenter, what that's going to do, if you remember, that's going to allow me to draw a circle that passes through A, B, and C. Is it okay? All right. Now, so when I can post some stuff for you, there's going to be questions like that, and your points that they give you are, unless it's created by me, which right now I'm not going to give these to you. If they're written by Math Excel, they're going to be a right triangle. You just got to figure out which segment is the hypotenuse and then find the midpoint of that segment. If these points were like that, still a right triangle. Still a right triangle. Do it that way. If our points were like that, okay. Actually, those weren't right triangles. Those were the wrong thing. If our points were like, that's stupid. If they were like that, okay, then the perpendicular bias of the circumcenter is going to be this point right here, which if we wanted to find that point, then we would have to be able to find these two equations. Okay, which if you remember at the end of chapter 3, we started doing some equation work. We will probably maybe do 1 or 2 examples of this in the coming days. But does everybody understand the difference between an in-center and a circumcenter? Okay, in-center and circumcenter. So let's stop there for today.